So this lecture is going to focus on count data models. We'll talk a little bit about Poisson and negative binomial regression. This is going to be pertinent, I suspect, for at least a few of your term paper projects. And so, like I said, we'll introduce both of those modeling frameworks, and then we'll largely work through an in-class exercise using a data set that we've published on previously, used for developing these types of models. And one quick note as it relates to the term paper for the course. So initially, the course schedule is such that we would have presentations during class session next week, so Monday and Wednesday. Based on where people are right now, I don't think that's really practical. And so what I would suggest is that we have those presentations submitted by the end of next week, so April 23rd. And then we'll basically have to rely on the students watching the presentations over that weekend. So my apologies for that, but I figured that would be preferable as opposed to trying to get those done during the class sessions next Monday and Wednesday. So I guess, can we just, does that seem reasonable to everyone? So we'll have those presentations recorded and uploaded through D2L by the end of next week. And then just over the weekend, we'll have to go through and watch those presentations and give feedback. So I guess thumbs up. Any discussion on that? If anybody really wants to, I guess you could still wrap it up and get it done in time for next Monday or Wednesday. But just, I know a few of you, it took a little bit longer to get some of the data pulled together. And so rather than rushing and trying to get something in, I would propose we do that. I don't really have any flexibility, unfortunately, with the paper. So that paper will be due on the 26th, but obviously the paper and the presentation will dovetail together nicely. So the 26th is the day that the quote unquote final exam is scheduled. And so we'll just have the term paper due basically by midnight on the 26th. And that'll give me some time to go through and evaluate those before getting the final course grades out. Okay. Any questions on anything before we get into the lecture content? Okay, if not. So count data is something we run into fairly regularly in transportation research. So anytime we have data that's countable, so basically any data that's comprised of non-negative integers, those are referred to generally as count data. And so there are just a few examples indicated here. So the number of times a driver changes their route during a given week, the number of times they change their departure time, how frequently they use various types of ITS technologies. And then in my own domain, a lot of the safety research we do, we're interested in how many crashes occur on a road segment or at an intersection during a given year. And so on the surface, it would seem like these are data that are well suited for linear regression, but we do run into a few of the same sorts of problems we've seen in other frameworks. And so a natural question then is, well, what happens if we use OLS to this end? And we'll demonstrate that in a moment using the sample data set described on the following slide here. So we have some materials that have been provided on D2L, where basically we have an Excel database that includes information for crashes that are occurring near roughly 2,500, 2,600 schools throughout the state of Michigan. And so this was done as a part of our Safe Routes to School program here in the state. And so near each of those locations, we've collected census data to detail socioeconomic characteristics of each of the school districts. We have some very general information about the adjacent roadway, specifically what functional class it is as per the National Functional Classification System. And then most importantly, we have the number of pedestrian and bicycle involved crashes that involve children ages 5 to 14 that occurred within a 1 mile radius of each of those schools. And so from our perspective, what we're trying to determine is what factors increase or decrease the likelihood of these child-involved crashes occurring near schools. And so it was largely motivated by ensuring that children are able to walk and or bike safely to school. And so to that end, This is just showing you a summary of what those data look like in essence. So there were a very large number of schools that didn't experience any crashes over that analysis period, I guess, fortunately. And then, as is typical with crash data, we see a lot of locations that experience a relatively small number, 1 or 2 or 3. And then we have a significantly smaller number of schools that would experience a larger number of crashes generally. Okay. And so what we're going to do from there basically is I will pull things into remote desktop real quick, and we'll do a demonstration in SPSS to look at these data. So let me stop that share. Okay, and so you should all see my remote desktop file now. And so in here, we basically have various pieces of information. We have school district codes. We have the number of children, grades K through 5 and 6 through 8, and then the total of those two. We have the total population in each of those school districts. We also have the population in each of those aforementioned age groups. So K through 5 would be ages 5 to 9, 6 through 8 would be 10 to 14, and then there's some bleed over there as well. I think these are based just on census groups, and the 5 to 14 is the target age here. We have some details on the surrounding census information. So the number of families that are white among those census areas, the average family size, population density, median family income, the number of parents per household. And then, as I had indicated, we've got the national functional class of roadway. And so the roadways are either arterials, collectors, locals, or they're not an NFC class facility. So those would be really low volume local roads, for example. And our primary variable of interest here is the number of crashes. I've logged a few of these variables, and we'll talk in a few minutes about why that's useful. But the primary thing we wanted to start with here is we're just going to estimate a linear regression model to see how those data look and what some of the limitations are when we try to assess count data using linear regression models. And so, as we've done previously here, we will develop our normal probability plots and histogram, and we're going to save our predicted values and residuals for demonstration purposes. And we'll start with a nice simple model. We're just going to estimate the number of crashes based on the total population in those areas. And then let's say we'll also look at the functional class of the roadway, and we'll hit OK. And let me find my output window. There we go. Okay, and so unsurprisingly, we see that as the population increases, crashes tend to increase. And then as we look at the other variables of interest, we haven't seen significant relationships here with respect to those road classes generally, but what we're tending to see, even though these results aren't significant at 95% confidence, we do tend to see more crashes on schools that are located on lower volume local roads, and we tend to see fewer crashes on those that are located on arterials and collectors. And while that might not necessarily make sense on the surface at first glance, part of that relates to the manner in which they try to direct children to and from these schools. So generally speaking, if it's along a higher class facility, there tends to be more restrictions and more guidance, and you'll have things like crossing guards, and there'll be additional safety measures that are introduced. Whereas on the lower class local roads, it gets a little crazy. There's simply not as much control, and so there's more erratic behavior. And so based on some other work we've done, that seems to make sense. But as we continue on here, the normal probability plot looks okay, but as we look at the residuals here, sorry, the histogram looks okay, but the residuals, as you'll see here, we're starting to depart significantly from normality. And if we go into our chart builder, and we're just going to do a quick scatter plot, as we've done many times before, of our predicted values, our residuals versus our predicteds. And you see a very familiar trend to what we've seen when we work through logistic regression or the ordinal or multinomial, whichever of those frameworks we worked in. We saw the same general trend here. And the reason that we see that is because our distribution is essentially truncated here, right? We can't experience less than 0 crashes. And so if we look at these predicted values, there's a significant number of cases where we're predicting significantly smaller than 0 values, which doesn't make sense really. And then we see this persistent decreasing trend in the residuals as our predicted values increase. And again, that's largely reflective of the nature of this distribution. And so consequently, as you can probably see from this brief demonstration, ordinary least squares is not necessarily a great fit when we're trying to assess count data. Okay, and so with that, I'm going to pull it back into the presentation. Okay. And so alternately, the way we work through this, as you saw in the preceding slide, those data are very similar in nature. They look a lot like the Poisson distribution, which we've talked about several times previously in the course. And so to that end, there are a few features that are unique to crash data and various other types of data sets that are comprised of counts, where the Poisson distribution is a reasonably good fit. And so first of all, small valued observations are very common. So if you've got a lot of zeros, ones, and twos, like if you're trying to model baseball or soccer scores even, as opposed to the numbers of crashes. Those would be circumstances where the Poisson distribution is a good fit. And then once you get beyond those values, specifically as you get a little bit beyond the mean, those frequencies start to decline rather rapidly. And so they'll approach 0 subsequently. Now, if we compare this, we had just shown that it's not a particularly good fit for ordinary least squares. That changes a bit if you start to get very large mean values. So as an example, instead of looking at the crashes within 1 mile of a school during a given year, if we looked at crashes across an entire county or entire state or the entire country, those data would probably much more closely follow a normal distribution. So that would be a caveat here, like a lot of the other families of models we've talked about. It's a particularly big concern to choose an appropriate framework when your mean value and your sample sizes are relatively small. But as those increase, virtually everything starts to approach normality. But in most instances, that's not going to be the case. One other artifact of the Poisson distribution is that the average or expected value of that distribution is equal to the variance. And it turns out that's a useful assumption, but it can also be somewhat restrictive, which gives rise to the negative binomial model that we'll introduce later in this lecture as well, which is essentially a generalization of the Poisson model. Okay. So this is just showing you the distributions for various Poisson models, assuming some underlying rate lambda. And so again, what lambda is telling us is basically the average number of events that occur over any given time period. And that could be per day, per month. With crashes, we're typically talking either per year, or in this case, we've actually looked at the number of crashes over a 5-year period, because pedestrian and bicycle crashes tend to be relatively infrequent. And so as those mean values increase from 0.8 up to 10.5, you'll notice how the shape of that distribution changes markedly. And as that mean keeps getting larger and larger, this will gradually approach normality. However, at those lower sample sizes, that normal distribution is a very poor fit as compared to what we're seeing with the Poisson. Okay. And so just refreshing everyone's memory with the probability density function for a Poisson random variable. So we know from the Poisson distribution, we can calculate the probability of y taking any specific value. So in our case, we could determine the probability of any school experiencing 0 or 1 or 2 crashes. And that probability would just be equal to the exponential of negative lambda, where lambda is again that average rate per unit time, times that same rate raised to the yi power. So depending upon what we're trying to determine the probability of the number of crashes, that's what yi is here, all over that same number factorial. Okay. And as I had mentioned, the expected value or mean of that distribution is equal to the variance. And so those are both equal to that same rate variable that we can establish based on our data of lambda sub I, where I is just indicating that this is specific to some location or some observation I. Okay. And so what we do is we basically introduce a log linear model for that parameter lambda. Okay, so we can think of it essentially as we're logging that crash rate, and then the right hand side of the equation is just a linear function. And so since we're ultimately interested in what the impacts are on the crash rate rather than the log of the crash rate, what we do in essence is we just exponentiate both sides of the equation. And so the general equation we're working from is as shown right here. Okay. And so that has several implications, the most important of which is since we're taking the exponential, we're constraining those model forecasts to then be positive. Okay, so we can't experience negative predictions, which means that we're going to have model results that make sense, at least conceptually at the end of the day. Okay. And one thing to think about as we look at those model parameters on the preceding slide, and we've talked about this previously, it's the betas aren't as simple as a 1 unit change in X corresponding to a 1 unit change in our dependent variable. And so I'll just back up here real quick. So as we increase these X's by 1 unit, you got to keep in mind that we're exponentiating that result, okay? And so if it's a continuous variable, we can just take the exponential of that beta, subtract 1, and multiply by 100. And that would tell us what the percent change is, in this case, in the number of crashes we would experience for a 1 unit increase in X. If it's a binary indicator variable, it's similar, but the interpretation in that case, these are typically yes or no variables. And so, for example, if we looked at the variables we had related to the functional class of the roadway, that variable would tell us as compared to the other classes of roadway or whatever the baseline cases are that have been left out of the model. This is the percent increase or decrease we would see in crashes as an example if that condition were true versus not. Okay, so interpretation, it's somewhat similar to how we had worked through some of the other frameworks. Just keep in mind that since we're logging the crash counts or we're exponentiating the X's, it's a little one extra step basically to interpret those coefficients. Goodness of fit. So we're again going to be estimating these models using maximum likelihood. And so generally what we would do, the simplest case, we just estimate an intercept only model. And then as we add variables, we would evaluate the deviance statistic, which is analogous to the likelihood ratio statistic that we had introduced when we talked about various types of discrete outcome models. Okay, and so the null hypothesis here is that those models have equivalent fit, and what we would hope to see is as we add variables to the model, we're going to see that the full model, the log likelihood, is going to get closer and closer to 0. We'll get significantly better fit. And as in the case of the other examples, when we work through likelihood ratio statistics, our calculated test statistic here is chi-squared distributed, and its degrees of freedom is simply equal to the number of predictors in the model. Okay. Now, one concern that arises, and this was noted in one of the preceding slides, is that the Poisson assumes that the mean and the variance of our distribution are equal to one another. What tends to happen in practice is there are a lot of circumstances where that's a tenuous assumption. And so especially if you've got relatively low means in your data, so relatively low count values, there'll be a lot of variability, and you'll tend to see that the variance is oftentimes greater than the mean in that case. And that introduces some problems to us potentially. So we're basically tending to systematically underestimate the variance is what happens there. And in the worst case, that can lead us to erroneous or biased parameter estimates, incorrect conclusions, et cetera. And so in this case, we have extra heterogeneity, which occurs in the Poisson means. And so to address that, we introduce what's referred to as a negative binomial model, okay? And so all we're doing in this circumstance is we're just adding an additional error term, essentially a heterogeneity term to that model. Such that we now have a variance that's going to be larger than the mean count is. And so our probability density function changes as follows. We basically just add that error term, u sub I, into the numerator in these two locations. And what happens then to the shape of those distributions, if we compare the Poisson to the negative binomial, you notice the negative binomial is, again, demonstrating greater variability, larger variance. So the peak is lower, and we tend to have significantly larger tails here, which is reflective of the fact that we're more likely to have some of those extreme observations than we would be if we were working with just a Poisson model. And so this is all based on the same underlying hypothetical data set you see right here, okay? Interpretation is generally similar. Now there's an additional parameter that's introduced as an output to our statistical models, and that's alpha, and alpha is referred to as an over dispersion parameter. So that's basically measuring how much additional variability we're seeing relative to the expected or mean value, okay? And so as that alpha collapses down to 0, then we're going to simply find, so as this converges towards 0, the variance and the mean are going to converge towards 1, and that will just reduce back to the Poisson model that we had started with initially, okay? Interpretation of the model parameters is going to be the exact same. We're still exponentiating our parameter estimates, subtracting 1, and then multiplying by 100 if we want to get that in terms of a percentage, okay? As I had mentioned, these are estimated via maximum likelihood, and so I've omitted the large scale derivation here, but our likelihood function for the Poisson and negative binomial models are as shown here, and the log likelihood functions are included immediately below that. And so consequently, when we work through and estimate these in SPSS, it's using maximum likelihood in order to determine what the best fits are for the betas and also for the alpha, the over dispersion parameter in these models, okay? And so what I wanted to do right now, we're going to quickly jump back over to SPSS. And so let me quickly share my remote desktop again. Okay, and so when we want to estimate these count data models, we're going to go under Analyze Generalized Linear Models, and under that setting, again, Generalized Linear Models. From there, we're going to select, we have several different options here. That includes a Poisson and a negative binomial model. And so as a starting point, let's go ahead, we'll estimate the Poisson. Now in the generalized linear modeling framework, and I believe we've talked about this previously with logistic regression and a few other examples, we need to fill out the first 4 tabs here in order to estimate the model. So first of all, we've indicated we're estimating a Poisson model. Our dependent variable in this case is going to be the number of crashes near that location. Our covariates, I'm just going to use that same simple model we saw previously. And so I'm going to take the log of our population, and then I've got indicator variables for whether it's an arterial, a collector, or a local road. And so I move all of those variables over into our model here, and then I'm going to hit OK. And so we end up with our model output. And so again, our deviance statistic is as shown here. And so that's just a broad goodness of fit statistic that we're going to use. And so the corresponding, this is like the F-test we'd see in linear regression. So that chi-squared statistic is very large. We've got 4 predictor variables in our model, and that's going to be highly significant at any practical level of significance, okay? And so then at the end of the day, coming down to our model results, keep in mind here the functional form of the model. So this is our left-hand side variable here is lambda, okay? So the average number of crashes we'd expect to see at a given year at any site is going to be equal to the exponential of this entire function here. So our constant term is negative 3.44. And then these are the betas that correspond to each of those x variables, okay? And so as we look through these, we see results that are similar to what we had seen when we looked at the linear regression output. So even though we had some violations. We were at least moving in the right direction generally with those effects. And so in interpreting these parameter estimates, so we've logged the population here. So I've taken the natural log. And so this is something we frequently do in count data models. Keep in mind our left-hand side is a rate. So it's crashes per year. And so if we think about the context of this study, we would expect to see significant differences based on the population, right? And so in those instances, whenever we see very large changes in X variable, it's often appealing for us to log that to improve the goodness of fit. And when we do that, since we've essentially exponentiated that right-hand side and now we're taking the natural log, for those variables, this can be interpreted directly as an elasticity. And so what I mean by that, this tells us if we increase our population by 1%, we see a 0.425% increase in crashes, okay? And so that's an artifact of how we've structured the model here. And so if we hadn't logged that variable, we would have had an interpretation as in any of these other cases. We would have just taken the exponential of negative 0.06, the exponential of negative 0.145, et cetera, okay? And so when we look at these parameter estimates, if they're positive, that means that these variables are associated with an increase in Y or an increase in crashes in this case. And if they're negative, that means they're associated with a decrease in crashes. And so as we saw when we tried to run it as a linear regression, we do see that there's an increase in crashes on the local roads, a decrease on the collectors, and so forth. Now, a few of these variables are statistically significant now. And so this is under the Poisson framework, okay? We're going to revisit the same analysis, and we're going to use the negative binomial framework as well, okay? So I'm gonna go back to generalized linear models. And the only thing I'm going to change here, I'm going to go to the negative binomial with the log link function, okay? And so that's just basically saying it's a log linear model, but we're assuming negative binomial instead of Poisson. The one thing I'll note here, by default, it's going to constrain our value of alpha, our over dispersion parameter, to be equal to 1. Now I'll just hit OK here and we can look at what the implications of that are. And so now, as we scroll down to the model results, we'll see these are relatively similar in nature. Specifically, the parameter estimates are quite similar, but the one thing that's happened here is that our standard errors now are a bit larger. And so what's happened as a consequence of that, the collector road variable, as an example, previously was either significant or very close. So let's just scroll up real quick and see. Yeah, so 0.069, likewise, that local road variable, the p-value is 0.002. That's increased to 0.036. And so what that's reflecting is, since we're accounting for the extra variability in the model here, that means that our standard errors are now correct, whereas they were biased downwards previously. And so since we were underestimating standard errors, in the preceding analysis, we may have found statistically significant results that were essentially reflective of type 1 errors, okay, because we weren't appropriately accounting for the additional variability in the model. Now, one thing I should note here, though, is this parameter right here, our negative binomial parameter, or alpha, we've constrained that to be equal to 1. So it's unclear here if that's a good assumption or not. So we can actually estimate a slightly more flexible model even. And so if we go under generalized linear models, we can construct a custom model. So we're going to do the same negative binomial with log link, but by default, it constrains that over dispersion parameter to be equal to 1. I'm not entirely sure, to be frank, why they have that option available to us, but in practice, we would generally estimate alpha as a part of our analysis, okay? And so in doing that, we're going to see a similar set of outputs here. You'll notice these parameters are generally, oh, what did I do there? For some reason. Oh, I specify value. I meant to estimate the value rather than to specify it. So by default, it'll specify it to be equal to 1. And so when we actually estimate that model, we see that that assumption of alpha being equal to 1.0 was okay, but when we estimate that as a free varying parameter, alpha is now equal to 1.25, okay? And so what that means is even in the preceding example, we had underestimated the amount of over dispersion, the amount of extra variance that was inherent in the model. And so when we do that, even the local road variable is no longer significant at 95% confidence, although it's reasonably close there. The strongest predictor in this case is that population variable, obviously. And in each of these cases, it's somewhat interesting to note the parameter estimates really aren't changing all that much. It's really the standard error that's changing significantly. And so that's the one big distinction between the Poisson and the negative binomial. Now, we will tend to see some shifts here in these parameters, but the biggest takeaway is if we assume a Poisson and there is extra variability, extra heterogeneity in our data, we do tend to overestimate the statistical significance of these parameters and are more prone to type 1 errors, okay? And so we can continue building through this model. Unfortunately, with this data set, we don't have a whole lot of flexibility. We've got a few census variables we could evaluate, for example, and things of that nature. But this gives you a very brief introduction. So you've got enough information to start working through this, as I know several of you do have data that are well suited for count data analysis. And so I guess at this point, I would welcome any questions that anyone may have on the count data models. And then after that, I do have one additional set of PowerPoint slides I'd like to work through as well. So any questions on the count data work we've presented up to this point?